there's actually only one slide with an equation on in this talk, so you'll be very relieved to know you can sleep through most of it and just concentrate on the pictures. Although the question is a fairly important one, especially for you guys, because you've got to cope with the problems that my generation has left you. So, sorry about that. So, global sustainability is probably the biggest problem that faces society and science in the current time, and this has been recognised at various levels, not necessarily by individual governments, but by the UN certainly. And they've had they produced before year 2000 the Millennial Development Goals, and these have been replaced now by the Sustainable Development Goals. And these are a set of targets which are supposed to be achieved by around 2030, and they've been signed off by 119 nations across the world at the UN. And they're all wonderful aspirations, and I think we would like all of them to be achieved. But there's a problem when you consider how to achieve these things, that they're all, in effect, manifestations of the way the human Earth system works. That's the intersection of society and the biophysical world. So all of these things are coupled at certain levels. So to understand whether you can achieve the Sustainable Development Goals, you really need to understand how the human Earth system, understood as a system, actually operates. Now, a different way of framing, a more scientific way, if you like, of framing the problems of global sustainability was proposed by a group from the Stockholm Resilience Centre, or organised around the Stockholm Resilience Centre, and led by Johan Rockström, who produced this paper, very influential paper in 2009, called Planetary Boundaries. And the idea was, can we define a biophysical safe operating space for humanity on the planet, and then ask, are we likely to stay in that safe operating space, or are things that we're doing going to move us out? And they defined operationally the climatological safe operating space as the late Holocene climate, the last 10,000, maybe 12,000 years. And demonstrably that is a safe operating space because all of human civilization arose in that period. So empirically it's a safe operating space. So if we can understand the biophysical parts of the planetary system, are things that we're doing likely to push us out of that? And they defined 9 critical parameters and then asked, are those parameters exceeding bounds which might push the system into a new and worse state? And he said that already 2 of these things, in other words, let's see if I can actually read them on here. It's very difficult to read this thing, isn't it? The human increase in the phosphorus and nitrogen cycles, which has been completely swamps the natural cycles. The loss of biodiversity. We're in one of the great geological extinction events at the moment, and climate change is heading towards towards crossing irreversible boundaries. Now, this paper got a lot of attention, but it prompted another influential paper by Kate Raworth in a discussion paper for Oxfam. And Raworth pointed out that as well as a biophysical safe operating space, we have to think of a social safe operating space. What kind of societies do we want in the future on the planet? And so she defined a whole set of properties of this safe operating space, so some physical things, food, water, health, but then more high-level things like gender equality, jobs, voice, resilience. And the problem is, while the biophysical safe operating space of Rockström et al. Could actually be understood as attributes of a dynamical systems description of the way the physical planet works, or the biophysical planet works, Kate Raworth's set of boundary parameters actually belong at different levels on things like Maslow's hierarchy of needs. If you look at what society or individuals need start to operate in life. There's some basic physiological needs, like you've got to be able to breathe, you need food, water, and so on. Safety, security of the body, of employment, of resources. And as you go up these higher levels, up to things like esteem and self-actualization, I'm not saying these are a good or necessarily a useful ranking, but nevertheless it shows that the Raworth boundaries fit at completely different levels. So finding a dynamical systems description that actually has those kind of indicators or as parameters, very difficult to do. In a sense, it's just like the UN Sustainable Development Goals. They belong at different levels of a hierarchy like that. So the question we face when we're doing this kind of work is, how can we describe the dynamics of this intersection of human society and the biophysical world in a way which gives us some useful insight as to whether we can find or define a planetary safe operating space that preserves both the physical necessities of life and the social necessities of life. So as a starting point for this, if we want to think of this as a system, it's usually stated almost now as a truism that society is a complex system. So let's start by asking, what is a complex system? We've used that phrase quite a few times already in this meeting. Well, when we started the CSIRO Complex System Science program, a dozen years ago now, we actually had some money to spend on projects. And so we were faced with this question of, when people propose projects, is what you're proposing about a complex system or merely a fiendishly complicated system? So what's the difference between an incredibly complicated system and a complex system? And we decided that really there are two attributes that make that distinction. So we could say to someone, well, that's a really interesting problem, but it's just a complicated system. Bugger off, you're not getting any money at all. But this is a complex system, you can have some money. And those two properties are emergence and self-organization. And we've talked about this before. Emergence, the whole is greater than the sum of the parts, which is easy to say, not so easy to define. And self-organization, that the system spontaneously tends towards some level of ordered organization. So emergence, it's useful to take a thermodynamic view of this idea that there are many microstates, many ways you can arrange the bits of the system but still produce the same overall macro outcome. So I think I talked before about snowflakes. You can start to arrange the atoms of water when the temperature drops into patterns, and that sort of breaks the symmetry of water molecules, which can otherwise be in all sorts of states. So it doesn't really matter which atoms you have, they still organize themselves into snowflake patterns. Or move up a bit into a biological example. So termite mounds, ant colonies, beehives. You've got lots and lots of individuals. Okay, bees themselves are pretty complicated things, but nevertheless, they organize themselves with just a few kinds of bees, some drones, some workers, and a queen. And it's actually the interaction of many, many individual units that give you the emergent property of a beehive. It's got a group intelligence or emergent intelligence. In fact, complex system scientists often talk about the ant-queen fallacy, the idea that the queen controls the whole nest. In fact, the queen is the dumbest thing in the nest, really, or it's just an egg-laying machine. So it's actually the interaction of many subunits, bees or ants or whatever it may be, with just a few types that give us this emergent intelligence that can reproduce, swarm, look for food, and reproduce itself. So it doesn't matter, you could exchange any of the drones for any other drones and the thing would still work like that. But drop down or go up, if you like, to humankind, so social systems. These are emergent properties of people living as a social animal on a landscape. And quite interesting, if you go back and look at the philosophers of the 18th century, people like David Hume and Hobbes, his famous book, The Leviathan, regarded men as in continual competition with each other. And in Hobbes' case, you needed the Leviathan, the ruler, to bring some order to this system. Whereas Jean-Jacques Rousseau said that humanity, or humankind, is actually a social species, and its tendency is to live and find ways to organize themselves. In fact, Rousseau was right. Hobbes and Hume were wrong. So we've seen as society has evolved from hunter-gatherer bands, which will form in extended family groups, as there was more surplus of food and a more sedentary living, they would then move into tribes, a greater level of organization, and eventually kingdoms, empires, and so on. And we have emergent technologies. When we have groups of people living together in some kind of system and needing to communicate and manage productivity, we have social technologies emerging, like currency, economies, religions, which are things which are emerging over and over again when we have society, humans living together in society. We'll come back to that. The other thing is the self-organization. Sorry, I won't come back to that. Let's carry on with this a bit longer. Self-organization. And this really goes along with the concept of attractors. What it means is there are some preferred states that the system would like to be in, and its internal workings will drive it towards that, to that state. So as I said in that earlier lecture, physical systems often seek configurations with the lowest energy. So all these molecules of water interact, and there's a tendency to drive them into patterns which reduce the chemical potential energy, or the interaction energy, the van der Waals forces. It takes extra energy to move the system out of these low energy configurations. So, as I say, we just add heat and the snowflakes melt, become, again, just a bunch of disordered water molecules. But in the case of human societies, villages, towns, and cities are actually attractors in the case of people producing a surplus of food on the landscape, which was essentially humankind after the Neolithic Revolution, the invention of farming and pastoralism, and then solving the problem of how to live on that landscape optimally. So villages, towns, and cities provide cooperative labour. It allows specialisation, security against predation. It means you can also get a gang of the lads together and go and predate someone else's surplus. And we have this, what I like to call the Great Perd experiment, where 12,000 years ago at the latest, humans moved across the Bering Strait into the Americas. This is in hunter-gatherer times, and then continued to develop independently in the Old and New World after the end of the last ice age. But when the Spaniards went to America, when Columbus crossed the Atlantic, and maybe when the Vikings went earlier, the Vikings didn't really encounter this. What Columbus found was, and the rest of the Spaniards and the Portuguese, were cities, empires, economies, religions, which were perfectly recognizable and completely parallel to the things that it left behind. In fact, in many ways, more advanced. Mexico City was much bigger than any city in Europe at the time, and much better furnished with sewerage systems and so on. So political systems, tribes to empires, urbanization, economy, religion seem to have emerged spontaneously. So we can say that they were attractors for human society, where people are living together, dealing with violence, dealing with sharing a surplus of food, producing technology which allow that to be managed. So what do we mean by an attractor? So Wilfrid showed a different cut through the Lorentz attractor. The Lorentz attractor, Ed Lorentz, as Wilfrid said, was modelling a very simple system, a thin layer of the atmosphere heated from below, and found that he could describe this by three coupled differential equations. and with three parameters: the vertical temperature profile, the intensity of the convection, and the temperature difference between the ascending and descending plumes of air, the kind of stuff that Matthias and I talked about yesterday. And if you do that and allow those three axes, the three variables, to define what we call a state space, so one point in that space defines the state of the system, at least as to this level of resolution. And then you let time go on and see how the state of the system evolves. And what we find in something like the Lorentz attractor, or the Lorentz system, is that the trajectory, wherever you start it, ends up on this complicated so-called attractor, where the system, all those lines are what happens as time goes on. The state of the system goes round and round and fits in this confined region of state space. Now, there's an important point here that these are quick chaotic systems, in the sense that if you started the system from two slightly different starting points, again, as Wilfred said, then the trajectories have to diverge exponentially. The so-called Lyapunov exponents are positive. Two states of the system will continue to diverge exponentially far apart. However, because they're on an attractor, they've got to stay within a restricted region of state space. So the climate changes, and we can't predict the weather very well after a few days. But nevertheless, the atmosphere isn't going to spontaneously freeze solid tomorrow or boil. Basically, we're stuck within some restricted region of the possible state space. So how do you reconcile these two things, that the trajectories get infinitely far apart if you go for long enough, but you're still going to stay within some restricted region of what the state of the system can be? And you get away with it because the surface of the attractor is a fractal. So think of it, if you like, as an infinite number of onion skins. So you start off, two trajectories start off, they go farther and farther apart, but they're going to cross again, but now they're on different onion skins. So measured along the surface of the attractor, you can get infinitely far apart, but still stay within a restricted part of the state space. And this is an important property of attractors in complex systems, that you can stay in a restricted part of the state space, but still be chaotic. And we can plot that like that, the graph on the left. So if you like, complex systems live somewhere between simple systems and completely chaotic systems. So they have some order. They have a emergent, so self-organized state they like to be in. Basically, they like to be on an attractor. And yet they're still random and chaotic, and the two things are possible to be manifested at the same time. So with that little bit of background about that's enough. That's probably all we need to know for the moment about complex systems. Let's look at the history of the world for the last 12,000 years. So we can, if you wanted to summarize the history of the world in two sentences, you could say that for 10,000 years nothing happened, and then in the last 200 years everything happened, which is, slightly glib, but not that far from the truth. So we go back to the agricultural revolution, the Neolithic revolution, where people started to domesticate plants and animals. And then we look at the way both population and technological advances evolved for the next 10,000 years. The growth rate of both the population and of wealth was infinitesimally small. A peasant in China in 1000 BC was just as well off as a peasant in Europe in 1000 AD. Really, for the certainly, empires rose and fell. Great art was produced. Some people were incredibly wealthy, but for the majority of population, nothing much changed until the Industrial Revolution, when suddenly we had this explosion of population, of economic output, of the rate of technological production, of technology production, and note also that we're including here both social technologies as well as physical technologies. So we almost have a bifurcation where a long, long period of stasis from the first revolution, the Neolithic revolution, to the Industrial Revolution, then we have this sudden abrupt change, which is why we call it a revolution. so this is the second of the two graphs, we can look at global population and global wealth by GDP. So again, we can see from this that the per capita GDP grew faster than exponential, and as Gabby said, in fact, the population has grown faster than exponential in recent times. So if we looked at, say, the populations of England, France, Germany, since between 1820 and 2000, the populations grew by about a factor of 5.5. The GDP grew by a factor of 100. So they got wealthier faster than population grew. So per capita GDP grew very fast too. So if we try to express this in that state space language, let's define the state space now, between which has three axes: population, per capita income, and the impact of humans, economic activity on the biosphere. And for 10,000 years, humanity rattled around in this little space near the origin, until in the Industrial Revolution, we suddenly lost, we left that attractor. So it seems empirically we were on some kind of an attractor, and then we went off the attractor in the Industrial Revolution and moved from having very low per capita wealth, very low population growth rates, very low technological advances, and now we're at a position where the average per capita wealth in the world is $15,000 US. It's in 2015. Not everybody gets that. Most of it is owned by a very few people, but leave that aside. The population has gone up to 7 billion plus, and we have now a substantial impact on the biosphere, with 3 of 7 planetary boundaries exceeded. So what happened? We can ask this question, okay, if we were on this attractor for so long, for 10,000 years, what was the nature of that attractor? What kept humanity rattling around near the origin for so long? And what we can point to is what we call the Malthusian attractor, or the Malthusian trap. It's been a societal attractor in this 2 of these axes, this population versus wealth space for those 10,000 years. And how does it work? Gabby said in his first lecture, he talks about the famous essay on population by Robert Thomas Malthus, who was an English clergyman, writing just about at the end of the pre-industrial time. So his essay on population came just as the Industrial Revolution was beginning to start. I think the Industrial Revolution is usually dated to begin in 1775, when the iron bridge was erected over I think it was the Derwent in Shropshire. So it's the first bridge made completely of iron, and it's in a town which surprisingly is called Ironbridge. So it was, in a sense, writing about something which had ruled society for all that previous time. And the nature of the Malthusian attractor is this, that it's got 3 essential principles. That birth rate or fertility increases with income per person, that the death rate or mortality decreases with income per person, but the income per person is inversely proportional to the population. So effectively, the population is sharing a fixed resource, or a resource which isn't growing fast compared to the rate that the birth and death rates. And in fact, I've drawn it all with straight lines here, but about the same time as Malthus was writing his essay on population, Daniel Ricciardo was producing his essay on what he called the iron law of wages, or diminishing returns. So basically all it says is that anything you're doing, if you do more of it, the return you get from it is less than, let's say you double your effort, you'll get less than half the result out of it. And that basically fitted just with Malthusian economics. So let's see what happens. If you imagine that something increased the birth rate at the same income per person, so people now are having more children at the same income, the population will rise, and because the population rises, you move up this curve, this bottom curve is called the technology schedule, and you end up with a new income per person at this equilibrium point where birth rate equals death rate, so stable population. That crossover point is called the subsistence income. You end up at the lowest subsistence income. So the result of an increase in birth rates at the same, everything else being equal, is that everyone gets poorer. And in fact, if you increase the technology that you have, so you move one of these curves up, then you get the same result again, that everyone gets poorer. So in fact, the actual population is determined entirely by this curve, the technology schedule, but the income per person, or the subsistence income that everyone has at this crossover point when population is stable, is determined by the birth and death rate schedules. And this is a very robust attractor. You can invent new technologies. You'll still get pushed back to the subsistence income point, and you can have some people creaming off a lot of the wealth to build themselves pyramids or palaces or whatever it may be. You still get the same result. So this is a very stable and strong attractor which kept humanity pretty much in that state for those 10,000 years. There are wrinkles around it, of course, and the things go up and down, but something happened in the Industrial Revolution. And suddenly that iron law of diminishing returns, that technology schedule which related the economic output and made it inversely proportional to population, was broken. But just to show that that was the way things worked before then, this curve here, this trajectory with time, is what happened to Britain in the plague years, 1350 to 1700, when the Black Death arrived from the Middle East, bubonic plague. And what happened was there'd be a wave of death. 40% of the population died in the first wave of the Black Death. The population dropped. Because the population dropped, the per capita wealth increased. Technology didn't change much in that period, and so you went up and down this line. So the only thing that improved the per capita income of people was to lose a lot of people in a plague event. So when a lot of people died, everyone that was left got wealthier, and then the population grew again and everyone got poorer. So you went up and down this line, but this inverse curve between population and real income. Then something happened and decided to move out of that, and in the Industrial Revolution we have the opposite. We have that the real income per capita starts to increase with population, a total reversal, and that broke the Malthusian attractor, and we're still now moving on that trajectory. The question I'll ask you towards the end of this talk is, are we moving on to another attractor, or are we still in transition to somewhere? Where might that somewhere be? So in the post-industrial world, which we're in now, if you like, we're not entirely dependent on simple industrial output. We have to add another axis to this state space. So we've got population, economic output, the state of the biosphere. I should have said that during those Malthusian years, the impact of humanity on the biosphere was relatively small. I mean, to be sure, people screwed up their local environments, but on a planetary scale, they didn't have much deleterious impact on the planet. They had some impact. There's a theory which is pretty much accepted now, I think, by Ruddiman and co., which said that from the growth of farming, particularly in the last 3,000 years, we have seen a delaying of the next ice age, which the planet will be naturally slipping into, because of methane production through farming systems. But it's only in the last 50 years or so where the rate of human impact on the planetary environment has taken off to the point where the human impact is comparable to natural impacts or natural systems. And this new era, or epoch rather, is being proposed to be called the Anthropocene. We'll come back to that in a moment. But clearly, societal state is one of the key drivers or key variables now that we have to consider, especially if we want to define a state space which allows us to answer this question of Raworth's: can we find a safe operating space where both the biophysical and the social desiderata are satisfied? So what I'm going to try and do is construct a systems description of the planet based on 4 state variables. There we are again: population, economic output, societal state, and impact on the biosphere. And there'll be 3 linking processes which turn out to be essential: inequality, urbanization, and energy provision. So what I'm going to do is go through those state variables first and describe basically the individual dynamics of those things, and then we'll start to put them all together after a short break. So let's start with population. The balance between fertility and mortality is strongly linked with per capita wealth. So this graph, there are graphs like this you can reproduce, or you can construct over time and over space. So this is a global graph from 2009, but you can actually go back over the last 150 years and you'll do a similar kind of result. So what we see is that the strongest correlate with fertility is per capita income, and the per capita income of a couple of $100, women during their childbearing years on average can have as many as 7 children. And that's still true of some parts of Africa. Nigeria, for example, is the fastest growing population in the world at the moment, and fertility rates in parts of Nigeria not quite up to 7, but they're very high. When you get down to a per capita income of around $5,000 per year, that's year 2000 US dollars, you find that the fertility rate, or total fertility, has dropped below 2.1. 2.1 is usually regarded as replacement rate, allowing for some inevitable infant mortality. So anywhere below that, populations will start to shrink. And in fact, in Europe, particularly if you leave aside immigration from the less developed world, the population of most European countries is actually shrinking. There are some outliers, and some of those outliers are caused by social effects, and we'll talk about those too. So, but the causal relationships between per capita income and fertility are both complicated and also not fully understood. So we will look at urban versus rural location and its impact. Culture and societal state. I can see where the USA is on that, but the USA has a relatively high fertility rate for a highly developed OECD country. I think, the USA may be the one way over on that's Europe on the right-hand side. Israel is a wealthy country, but it has a kind of settler mentality or culture, which tends to higher birth rates and so on, but also immigration, more recent immigration from less developed parts of the Middle East have also led to higher birth rates. So you've got that mixture of cultural factors and other things. Let's look at the mortality, which is pretty much the inverse of fertility. And at around $5,000 income per year, you've reached a life expectancy of the mid-70s, and it flattens out after that. There aren't that many people living to 150 yet. Maybe the very wealthy will do soon, but pretty much those two curves are inverses of each other. Now, what happened during the Industrial Revolution? We talk about the Industrial Revolution. Actually, it was a revolution in several things. There was a demographic transition, the second demographic transition. The first one was at the Neolithic revolution. There was an urbanization transition, and there was a transition in equality, or rather a growth of inequality. But the demographic transition is the key feedback in population. And what happened was that when mortality fell, a generation or two later, fertility fell. And there are a series of factors which drive this, but urbanization is part of it. But the way this is usually explained is that if you don't need to have 5 children to provide your social security in your old age, you can have fewer children with better health for everyone involved and concentrate your resources on giving them a better life. Now this becomes, that's a sort of high-minded feedback, but in fact urbanization and industrialization give you a very strong Darwinian reason for doing this, in as much as children are an economic burden in an industrial setting until they're old enough to start having a job. Now we read about 5-year-olds working in the factories, but there weren't that many of those. In fact, if you go into rural settings in the non-developed world at the moment, you can still see 5- and 6-year-olds herding the geese. Go trekking in Nepal, you'll see that. People can be productive in a rural setting at a very young age, but not so productive in an urban setting until they're somewhat older. So this allowed a very strong Darwinian feedback mechanism to have fewer children in an industrial setting. So during the Industrial Revolution, that decrease in birth rate, which followed the decrease in death rate 2 or 3 generations later, led to a drop in the population. To begin with, the drop in death rate accelerated the population growth. So where the gap between birth rate and death rate is largest, that's when the population growth rate is highest. But then when the birth rate drops down to match the death rate again, the population will level out. Now at the moment, we're seeing a demographic transition in the rest of the world, which, following the one that occurred in the industrializing world in the Industrial Revolution, the time delay between the drop in death rate and the drop in birth rate is much faster now. It's about 1 generation, not 2 or 3 generations. But demographers talk about the amplification factor, the difference between the stable population after the demographic transition and that before. And we saw amplification factors of 2 or 3 in the industrializing world during the Industrial Revolution. Now, in that faster demographic transition we're seeing at the moment, the amplification factors can be higher. So in Mexico, for example, which has gone through its demographic transition, the amplification of population was about 5. So as we look at stable populations in the future, maybe by about 2100, where the UN models predict the population flattening out, it assumes the demographic transition, but even after the demographic transition has gone past, population growth continues to rise for some time through what's known as population momentum. There are more generations alive at the same time having children. So you can get birth rates equal death rates, but still the population will grow for some time after that. There's an effect of urban living. So empirically, in people of the same socioeconomic level in an urban setting tend to have fewer children than the same socioeconomic groups in a rural setting. And at the same time, infant mortality or mortality generally is lower in an urban than a rural setting, usually to do with access to medical services, to better water supplies and so on. It's interesting, it's not clear whether these data, which have been collected over quite a period of time in many different places, actually properly survey the what do you call them, the slums around the emerging megacities, so the favelas in Rio and so on, or the slums around Nairobi or Lagos. So it may be that these data are actually a bit skewed, that the people who live in privation on the urban fringes don't obey this thing. But nevertheless, for people living in a proper urban, well-serviced setting, these relationships seem to be fairly powerful and certainly worked through the Industrial Revolution. So that was the first thing, population, the key things about that. Basically, the relationship to per capita wealth or per capita income and the demographic transition. There's a sort of a corollary to this before we move on to this, which is that in order to get the kind of flattening out of population that the UN models assume, implicitly we need to actually get average per capita wealth up to that $5,000 per year. Very hard to do that if we maintain the level of inequality we currently have, because then instead of having to increase economic output by 3 or 4, we have to increase it by about 30 or 40. So we have to basically reduce inequality as well as increase economic output. So we can't actually flatten out population as long as these laws, these empirical laws, relationships continue to hold, without substantially increasing economic output. So basically saying that we've got to slow down economic output or growth doesn't really answer the problems that we have. If you make people poorer, then they end up having more children. So the generation of wealth, let's look at this one, the second of the state variables. And this is the only slide with any equations on it. So let's write a very simple description of the global economy. And this is in per capita, all in per capita terms. So the economic output is given by some function, some unknown function of capital, the amount of investment you put into your economic output, and land or natural resources. And these two things, capital and natural resources, is converted through this function with an efficiency A. And we can look at growth rates in all of the bits of this equation, define the growth rate as the change, the differential of one of the quantities divided by the actual magnitude of the quantity. So if you do that, just take the total differential of this thing and expand it a bit, we find out that the rate of growth of economic output can be written as the rate of growth of capital times if the thing is at steady state, as it was for that long 10,000 year time, times the return to the owners of capital, what economists call the rents on capital, plus the growth rate in land or natural resources times the return to the owners of land, the rents on land, plus the growth in the efficiency with which these inputs are converted into outputs. Again, all in per capita terms, which is why we don't have labour in explicitly in this formula. So in that Malthusian time, the growth in output and in capital was effectively zero for all that time. So the growth in efficiency of production can't be any faster, here we are, than the growth in population. So you linked, that's why you had that inverse law. You basically can't break that link between population growth and efficiency growth. And it's an inverse relationship. But then we saw that change in the Industrial Revolution in the modern age. And now we have a different situation. It's easy to have lost an equal sign there, sorry. The growth in output now is mainly the result of improvements in economic efficiency. So we see that the supply of land or resources is no longer the critical limiting factor. The dependence on reinvestment in investment of capital into economic output is about is responsible for only a quarter of the growth in output, and the other 3/4 is achieved by the growth in the efficiency with which inputs are turned into outputs. So we had a fundamental change in the way that economic output is produced after we've gone through the Industrial Revolution. This is perhaps the most novel part of what I'm going to try and tell you. How do we include societal state in the model of this kind? Normally what we do is leave that outside the model. It's a deus ex machina. That's why we have planetary boundary papers which are about the biophysical planet. When we do predictions of future climate, Wilfred showed us some error, the spread in predictions of what the future climate might be, and how those were most of the uncertainty was in our estimates of what the future greenhouse gas emissions from global economy would be, because we don't have good understanding of how humans are going to behave in the future. But if you want a model that pulls in everything, just to see if there might be some unexpected feedbacks or consequences that we should be aware of. Maybe I should have said this at the beginning. Let's just step back a bit. If we think of what climate scientists did with climate science, basically to warn the world that continuing to pump greenhouse gases into the atmosphere at the rate we're doing potentially could change the climate and cause serious impacts on global society, and therefore we should do something about it. In essence, what we did was to try to understand what was going on and to produce a warning. What we're trying to do here with work of this kind is to say, well, if we put together everything, are there some things which we have not anticipated that society actually should be aware of? So if you keep the humans and the human behavior outside the model, you may be missing some critical feedbacks which we were not aware of and weren't therefore taken account of when we do things like produce global policies like the UN Sustainable Development Goals. So we have to put in societal state, political dynamics, if you like, in some way. So what I'm going to present here certainly may not be the only way we can do this, but it is a way which actually fits with the rest of this model and gives you some idea of what kind of resolution of these processes you need to have in a model of this kind. So Douglas North and Wallace and Weingast or Francis Fukuyama, you may have heard of, he wrote a famous book called The End of History, when the Berlin Wall collapsed. It turned out that history is still going on, apparently. But, nevertheless, he's a very good thinker and in this whole area. But anyway, the North, Wallace and Weingast work, a lot of it's encapsulated in a book called Violence and Social Orders. And the basic thesis behind this is that a lot of the organization of societies that we've seen through the development of society has been in order to manage violence, to limit and to organize violence. So otherwise, if you look at primitive hunter-gatherer societies, the few that are left around the world, and look at the records, just honest records of the last 100 years or so, these are very, very violent societies. The murder rates in an Amazon, tribe is, an order of magnitude larger than even in Baltimore, or Chicago. So it's the idea of humans, sort of living in some Arcadian state, pre the growth of society, is absolute nonsense. The opposite is the case. So the idea of this, of all these thinkers, is that as society has grown, there has to be ways to sort of organize and limit violence. And I don't know if any of you are aware of a book called The Better Angels of Our Nature by Steven Pinker. It's worth a read. Pinker shows that on a per capita basis, we're now living in the least violent of times. If you go back to the times that on a global per capita basis have killed the most people, you'd need to go back to, I think there's a revolution in China about 1000 BC, but even the First and Second World Wars hardly score on a global scale per capita basis. And in terms of using judicial punishment, public torture, all that kind of thing, there are less and less, even though we seem to live in a very violent age in terms of total quantity of violence, the per capita rates are much, much lower. So we live in a pretty good time. So limiting violence and using violence can be a driver for societal organization. Anyway, North and Co. define 3 orders of society. The foraging order, which is how hunter-gatherer societies are organized, and we're not really interested in that anymore. What they call the limited access order, or the natural state, which has been most of society for most of history, including today. And then finally, open access orders were modern liberal democracies, if you like, and Fukuyama calls them liberal democracies, and his type specimen is Denmark. I don't know if there's anyone here from Denmark, but his view is that's a kind of the modern liberal democracy where most of the kind of things that Kate Raworth would have liked to see in a safe society are actually manifested. Obviously not for everybody all the time, but nevertheless. So the natural state, or the limited access order, say 10,000 BC to now, That's a very long time. So North is I'll divide this into three subsections: the fragile limited access orders, so early and primitive societies; basic limited access orders, kingdoms, empires, right up to the present day, of course; and mature limited access orders, so modern policies but lack some of the basic freedoms that we would see in a liberal democracy. So you might look at China today, the USSR, into modern Russia. And these limited access orders are characterized by slowly growing economies, which are vulnerable to shocks, often planned economies, government without the general consent of the governed, relatively small numbers of organizations operating in society. In other words, the term limited access means that you're not free to form an organization basically to compete in politics or in the economy. You only do that with the permission of the hierarchy. So social relationships are organized predominantly along personal lines. It's who you were born to, who you know, who you're related to, your own personal prowess that determines your position in society. It's the opposite of everyone being, at least nominally, treated as equally before the law. And we have smaller and more centralized governments. We have these organization of social relationships, laws that are enforced unequally, insecure property rights, and this pervasive sense that not all the individuals are created equal or indeed are equal. So, sometimes all these people who crave for smaller governments, and you maybe should tell them that a good example of a country with a very small government is Somalia. If you want a small government, look at what happens when you have a really small government. So the open access order, which really started to appear around 1850 to now, was modern liberal democracies. These are characterized instead by political and economic development, economies that on average experience positive growth, rich and vibrant civil society with lots of organizations. You can actually see, if you plot, look at societies around the world, you can see the step change in the number of organizations in an open access society or a liberal democracy compared to what we'd call the natural state or limited access society. Bigger governments and widespread impersonal social relationships. So the existence of what the sociologists call perpetual organizations. In other words, organizations, taking part in politics, the economy, and society, which don't depend on the individuals who run them, but are actually enduring even though the people involved in them move through. Now the question is, how do you get from one of these states to the other? How do you get from a natural state to an open access order? Well, first of all, you have to move out of the Malthusian state, which happened in the Industrial Revolution. This seems to require a quantum increase in production efficiency, and then the breakdown of existing hierarchical norms. So for most of societal time, or these 10,000 years, Fukuyama would say that society is organized with an elite ruling class and a servile, mainly agricultural, laboring class, and a few specialists like soldiers and priests and potters and what have you, but nevertheless a very strong two-layer society. So you require a breakdown not only in production efficiency and wealth, but the breakdown of existing social norms. This happened again in the Industrial Revolution. The Industrial Revolution in Britain was preceded by a series of things which drove people off the land, driven partly by the Napoleonic Wars and partly by increases in efficiency of farming, crop rotation. We had what was called the enclosures in Britain, where common land was enclosed and then used for crop production. And the people who used to depend on the commons to graze their few cows or geese were actually basically forced off into the cities. The same thing's happening now. In China, it's a kind of an attraction where, grinding medieval poverty on the land is replaced by opportunity in the cities. So we have this massive urbanization in China, which provides a kind of a safety valve for people which would otherwise be a very restive group. But in Africa, we're in an earlier state where people are actually being driven off the land, places like Sudan or Kenya or what's it called? Not the Portuguese place near Zimbabwe. Anyway, there are many examples where people actually, the land has been used for agriculture, often agriculture owned or driven by foreign interests, and people then end up being pushed into the fringes of the big cities like Nairobi and Lagos. So first we've got to move out of that Malthusian state, breaking down the existing social norms, usually by moving off rural settings where the social norms, the hierarchical social norms are into an urban setting where these things are broken down and new ideas come. Given that, the role of inequality then becomes central. So from a game theoretic point of view, you can frame this as a tension between the masses, who basically have nothing, and the elites who have most of the de jure power, the power on the law. The masses are capable of seizing de facto power for a time by having a revolution. But they don't want to be in permanent revolution. You've got to have a new de jure power. So the goal of the masses is to change the laws so that wealth redistribution continues even after the revolution. So you have this game theoretic balance where the elites have to make a judgment about whether it's in their rational self-interest to suppress the rebellion or to cede enough de jure power to the masses to basically avoid the revolution. And the countries which made a relatively smooth transition from the natural state, the limited access orders, to the open access order over the last 100 years, have managed to just cede enough at each step to avoid the revolution. France didn't quite get it right. They had the revolution. Britain just managed to avoid a revolution about the same time as the French Revolution by extending the franchise, which is the way the power is usually ceded to extend the franchise. And the US and so on have done this. So we have this game theoretic model that we can use to show how inequality, evident and sufficient inequality, can then drive the balance so that you either have the revolution or you don't. Now, the revolution can actually then be suppressed again and you can swing backwards and forwards, but you can treat this in the game theoretic point of view. Now, this isn't a new idea. So Plutarch said when will this be written? About 400 AD. The disparity of fortunes between the rich and the poor had reached its height, so the city seemed to be in a dangerous condition, and no other means for freeing it from disturbance seemed possible but despotic power. So what does that remind you of? You know, basically, when you push people to inequality, or you make people unequal to such an extent that they seize something, we sort of seen a reflection of the populism that we're seeing, I guess, in Trumpland, Brexit in the UK, but also what happened in Europe between the First and Second World Wars. If people are sort of repressed and unequal, they'll reach out. You might have a revolution, but the revolution may be take the form of electing someone through a democratic process who basically can then break the system, as Hitler did and as Trump's trying to do. So the stable transition from a natural state to an open access order requires 3 doorstep conditions. Rule of law for the elites. So the elites already have to obey the law themselves, so there is some pattern for extending this to the masses. Perpetual organizations I've talked about. Centralized control of the military seems to be the 3rd condition. So if the doorstep conditions are not in place, you can have the revolution, but what you get at the other end is chaos. So if we look at the Arab Spring, which seemed to be so promising, almost all the countries that went through the Arab Spring have either gone back to repression or to anarchy. And in many cases, we have these warring militias and so on. So, in terms of societal state, we have this hierarchy from different levels of limited access order or natural state, and then a transition into the open access order, which is then taking us to what what Raworth wanted in terms of a just operating space. May not guarantee a just operating space, but at least it's a necessary condition, might not be sufficient. It's what Karl Popper called the open society in his famous book or essay, The Open Society and Its Enemies. So this is the kind of definition of the kind of society we would like to live in. If the doorstep conditions are not in place, you won't get a successful transition, but it's inequality that drives that transition. And then finally, the biospheric state. So this is an update of the original Rockström paper by Will, Stefan and the same group, looking at where we are now in these indicators. So the phosphorus and nitrogen cycles have exceeded the dangerous level, which is this circle here. Genetic diversity, which is the way they've now rephrased the not biospheric integrity, number of species and so on. And some of the others are getting pretty close. Land system change, climate change, of course. So problems still with the biospheric state. And of course, we'll see how these other bits interact with that. So I think it might take 5 minutes. And then what we'll do is go through the way these systems interact with each other to give you some idea of what all the feedbacks and links are in this system and how we might expect the thing to behave as a complex system. Okay, take 5. Okay. Well, it sort of was obvious from the broad descriptions that economic output and population are interactive. Economic output is linked to societal state and also affects the state of the biosphere, which in turn affects population. But let's look at the more detailed interactions in each of these state variables. Let's start with population. So population obviously is the balance between fertility and mortality. Now, on each of these arrows, there'll be a plus or a minus sign, and that denotes that if the variable at the starting point of the arrow increases, then it will have a positive effect on the variable at the end of the arrow. So that's a kind of a convention. And well, if I remember, the yellow things are the state variables, the middle ones are the link processes, and I found I had to define some intermediate variables too, but there we go. So the basic feedback, as we said, between mortality and fertility is the demographic transition. If mortality drops, or that becomes negative, then it has a negative effect on fertility. Fertility will drop. But we also saw that per capita wealth, and we'll make that median per capita wealth, not the average, so get at least a little bit of a step towards looking at what the real per capita wealth of people is, will depress both fertility and mortality. But population's got to live somewhere, so if population grows, the urbanization will grow. The urbanization will have a depressing effect on fertility, but also similarly a depressing effect on mortality. So we have these basic links and feedbacks in the population system. Now look at economic output. The labor of the population is necessary for the economy, but also the capital. And the capital in the economic framework, capital is just people's savings. You put your money in the bank, hard to avoid it. Unless you put it in the sock under a mattress, then basically your capital is available for someone else to borrow and be reinvested in the economy, which is how you get some return on it. So population has a positive effect on economic output, both through capital and through the labor. Economic output, economy requires energy, so as the economy grows, it can invest in energy provision. Energy provision has a positive impact on the economy, so that's a positive feedback loop. Urbanization has been seen, through the Industrial Revolution onwards, to increase economic output by originally concentrating the means of manufacturing and getting efficiencies from having the manufacturing in one place. The cotton mills in the little town where I grew up, 200 years earlier, it would have been lots of cottage spinners and weavers. Suddenly they're all in a big factory powered by steam. So those are the key feedbacks in the economic output set of loops. If we now look at the societal state, this is a little bit more interesting. So as we saw, population increases the economic output. An increase in economic output, people are a bit wealthier, you increase the societal state, where a positive change in societal state means a tendency to move from the natural state towards an open access order, through the steps in the 3 levels of primitive, basic and advanced or mature natural state and then open access order. So think of that as an ordinal variable, maybe with 4 states, where the highest state is the open access order. So an increase in economic output improves that, but also an increase in the societal state has a more productive economy. And inequality is also important. So if the societal state is more advanced, then the inequality is less, but the level of inequality can be driving that transition from the natural state to the open access order. So an increase in societal state has a negative effect on inequality. Inequality has a positive effect on the societal state. Now, the level of inequality translates economic output into median per capita wealth. So if one person got all the output, wouldn't have any impact on fertility-mortality. Look at Saudi Arabia, where you have a very segregated, few people have all the wealth, you have high fertility and relatively high mortality rates in the population. So inequality becomes a filter by which economic output gets spread or not spread around the population. Then the median per capita wealth has those impacts we saw on fertility and mortality. And then the societal state itself can have a direct effect on fertility because of what society's expectations are. As we see, for example, in the southern states of the US, TFR is actually higher than in the sort of northern, northeast and northwest. There's sort of expectations of having more or fewer children, and we see these societies around the world. So we have, so let's go back a bit. So we have these fundamental links which determine the societal state. So the state of the biosphere. Again, economic output, obviously economic activity has an impact on the state of the biosphere. So not only through energy provision, but also through direct impacts on the biosphere, which are usually negative. The most extreme ones, let's think of an example, the dead zone at the mouth of the Mississippi, which extends almost 100 kilometers into the Caribbean. So basically the crap that comes down the Mississippi, which is linking the economic output of, to half of the US, kills life in a huge area around the mouth of the river. And also, farming, food production, especially as we start heading towards population levels of 9 to 11 billion, the amount of land needed to be sequestered for food production has had a massive impact on biodiversity. So the main cause of biodiversity loss in the world has not been necessarily specifically killing the last dodo or chopping the last tree down on Easter Island. It's actually been loss of habitat as land's taken over for farming. Interesting concept here. We talked about the Anthropocene. There's an Anthropocene working group which has presented to the there's a group of geologists who basically decide. Wilfred may know the name of this group, but the stratigraphic committee which decides how to name epochs in the geological record, and it's all according to the stratigraphic record. So the Anthropocene working group has had to present basically what the Anthropocene would look like when you dig it up, a million years from now. And one of the things that would be a mark of the Anthropocene is the uniformity of species around the world. So domestication of animals, particularly since the globalization, since the Second World War, has led to massive uniformity and monocultural crops and animals around the world, which is, totally unprecedented in the previous fossil record. Societal state affects the state of the biosphere. We're seeing at the moment, I don't know if you see it so much in Europe, but you certainly see it in the US and in Australia, a sort of an almost a relish with which the more extreme conservatives attack the environment. It's almost a badge that you wear as a right-winger, that destroying the environment is something that right-wingers do. I'm being a bit extreme here, but our colleague Mike Raupak wrote a beautiful paper called The Clash of Narratives. And Mike would propose that basically we have two ruling narratives, certainly in the West, about the way we view the planet. One would be the exploitation narrative, and one would be the nurturing narrative. So the exploitation narrative, obviously the planet's there for our use. Exploiting the planet economically has been enormously beneficial for mankind. Population has grown, far fewer people in poverty. We've eradicated diseases, many diseases and so on. People live longer, happier, healthier in the main. So it's been economic growth and exploitation has been a pretty much unmitigated success. The nurturing narrative basically, goes back a long way, of course, to perhaps the writings of Thoreau and Emerson, but particularly since the 60s, the environment movement has basically made almost, some people would say, a quasi-religion about caring for the planet. I wouldn't say that, because I think caring for the planet is a sensible thing to do. But when I was at uni, most students' bedrooms had that picture of Earthrise taken from over the moon from one of the Apollo spacecrafts. That was one of the things you'd see on so many bedroom walls. It was basically this picture which just emphasized the finitude of this beautiful little blue-green planet there. So the idea that we are in a finite planet. So those ruling ideas drive the green movement, drive the sensibilities of most young people, I would hope. So the way that the ruling ideas of society view the biosphere to be exploited or to be preserved has a major impact on the state of the biosphere too. The state of the biosphere can affect mortality. When things are polluted and so on, you can increase mortality. When you can't produce food, you increase mortality, droughts and so on. Urbanization can be positive or negative. So on the one hand, urbanization often takes over productive farmland. It can pollute waters and so on. At the same time, having all the people collected together in one place rather than spread thinly over the landscape is a positive thing. So urbanization can be good or bad, depending. In the same way as the societal state can be good or bad, depending on the narrative. So those links and feedbacks, when you put them all together, you see that things get fairly complicated. But you will have noticed, if you remember what I said about emergence, that all of these state variables and linking processes are all described at a fairly high emergent level. I haven't said as much, but basically we're looking at the entire globe or regions of the globe without specifying it very much. But very often, the actual interactions occur strongly at a finer scale. So the coupling between the impact of climate on the global economy happens not at the global level. If you want to see the strong coupling, you've got to drop down a couple of levels. So in order to actually make a model like this work, you've actually got to get in and look at the links and see where they were and how they work, but at the final level. Now I'm just going to give two examples which still use the same state variables, but look at how these work at a finer grain level, still at a emergent level, but less emergent than this. And the first one is the effect of climate change on its impact on global food production and food security. So what we've got here are two plots of the suitability of land for growing crops defined as agroecological zones. So the blue zones are boreal, green is temperate, red is tropical, and the density of the colour denotes the length of the growing season. And we're looking at a 1961 to 1990 reference case taken from IPCC AR5 data, and then what that would look like under RCP 8.5, the high emission intensity scenario, which is actually less than business as usual. The globe at the moment is tracking emissions, the global emissions are tracking higher than RCP 8.5. These are representative concentration pathways which are now used to drive climate models for comparison. So this is what the world would look like with a 4-degree rise in temperature. The shift in agroecological zones, you can look at the disappearance of the boreal regions in Canada and Eurasia, pretty much, the drying out of the Amazon and of southern Africa, and some other major shifts. And on the bottom left are changes in the productivity of different crops. So that's what climate change is expected to do. So how will this sort of impact food security? Well, at the moment, and for most of history, most food has been grown not far from where it's consumed, certainly in the same country. But more and more, we buffer the effects of local shortfalls in food by trade. And so it's not talking about aid, but basically trade in food. So trade then is linked to economic output, the ability to pay. But if we look at, let's see if I can do this now. If we look at the impact of things like El Nino, is the El Nino Southern Oscillation Index over time, we can actually link that together with other phenomena to changes in the complexity of the food trade network. So here are 4 examples of what the trade in 4 basic staple foods: rice, wheat, coarse grains, and oilseeds, which provide about 2/3 of the nutrition for the planet at the moment. So this is the way the trade in those things have changed. What we're plotting here is an index we've formed by taking, I won't explain it in detail, it would take a bit another seminar, but basically looking at the complexity of the global trade network and forming from that a single index which is related to Shannon's information entropy. So basically we look at how clustered trade is and whether trade is dominated by just a few countries or whether trade is evenly spread out. And that index we can plot, and we can see the First and Second World Wars, we can see the fall of the Iron Curtain, we can see a little blip from the GFC and so on, and some signal also from ENSO events. But that trade is what actually buffers current shortfalls in food around the world. And if we look at the change in resilience of the food trade network, considering both the impact of climate change on food production areas, as we've shown, but also the impact of the cost of mitigation on the economies of countries, which then drive the trade network. So when you put those two things together, we see that the resilience of the food trade network, which we identify with this index that we've formed, increases until about, can you see the date there? I'm standing right here and I can't see it. But it's about 2050 when the resilience of the food trade network starts to decrease in the unmitigated climate change scenario. Whereas if you mitigate climate change, where you actually buffer, you don't have as large an impact on the ability to grow food or change in the ability to grow food, but it costs you something, with a carbon price. But nevertheless, you start to get a positive gain by mitigation on this particular aspect of global change, which is food security, after about 2050, 2060. So that kind of thing, which of course feeds into the mortality thing, people don't eat, they die, and the biospheric state, the economic output and its impact on greenhouse gases and climate change are all linked at this kind of level, not at the global level. A second example is a little bit different, but again, I'm going to talk about coupling at a finer scale level. We'll look at the Syrian Civil War, and this you can construe as a result of demography, migration, climate change, inequality, and societal change. So basically everything. So let's start with the population. So if we look at the population pyramids in Syria, what we see is the moving through this population pyramid of a bulge of 15 to 20-year-olds. And this is a result, if you like, of exporting mortality-limiting technologies to the world, particularly after the Second World War, faster than we export fertility-limited technologies. So basically we have this growth of population. It's like the python that swallowed the pig. It's slowly moving through the system. But currently we've got this bulge in the 15 to 25-year-old age group. Now, the Iraq war caused a massive flood of refugees into Syria to escape the conflict. At the same time, Syria was experiencing a 10-year drought from about 2002 to 2014, which was a climate change signal, or part of a climate change signal, where we see the long-term drying in the fertile crescent. So that's dropping, in any case, precipitation and water tables. At the same time, there was this drive for agricultural self-sufficiency in Syria, and that led to a massive growth in the amount of irrigation. People were sinking wells into the water table. The drying of the landscape at the same time as this overuse of water without any real regard for how self-sufficient Syria could be in agriculture led to a bit of a crash, and the displaced Syrian farmers moved back into the cities. At the same time, there's 1.5 million refugees from the Iraq conflict moved into the cities. So it led to almost a doubling of the urban population in Syria between, I haven't got the actual numbers here, but I think it's between, they're on the, balloons from 8.9 million in 2002 to just before the US invasion of Iraq to almost double that in 2010. So you had these overcrowded peri-urban settlements, and they became the centers of unrest against this 40-year-old Assad regime. So basically, the country had just about tolerated it for all that time, but suddenly you've got these massive numbers of unemployed 25-year-olds, swelled by refugees from Iraq, and you end up with a civil war as the evident and real inequality tips the system against the elites. Now, the interesting thing about this as a lesson in the way these models can be useful is that while some of the events that led to this and eventually leading to the growth of ISIS and the refugee movements into Europe, while some of those events are contingent, like the US invasion of Iraq or the fact that Russia decides to intervene in the Syrian Civil War on the side of Assad, are pretty much contingent events, or the timing of the revolution is a contingent event. The growth in the, if you like, the cannon fodder for the revolution, if I can crudely call it that, the unemployed 25-year-olds, the economic downturn that made them unemployed, the collapse of Syrian farming caused by climate change are all perfectly predictable. So the kind of models we've been talking about are of the kind that you could use to see whether a system is being driven to a point of collapse. But of course, you can never pick the event that causes the critical thing to happen. So all you can say is that the system has now reached a critical state. But then, of course, you have to be careful. So we put all this stuff together, and the arrows that are in red are the ones we know least about. And surprise, surprise, the things we know least about are the social interactions. And I've used, as I said, a model. It's the kind of model which gives us the information that we want. So that's the level of resolution we need to have in any model of societal dynamics to link with the biophysical dynamics. But that's the most, if you like, shaky part of this whole system. If you were, if you like, going to start again by trying to understand climate and so on, maybe what you would be doing is saying, we probably know as much as we need to know about the biophysical aspects of climate. We need to be putting all our efforts into modelling the social dynamics which are driving greenhouse gas emissions. Given the warning that we have, why aren't we doing something about it? I lied, actually. There are two slides with equations. So we can examine our system for instabilities, tipping points, bifurcations, all the stuff that Gabby talked about in our first day. Even though our knowledge of the functional relationships may be rather limited. Because, as Gabby said, in that first talk, you can take a function that you don't know very well, expand it in a Taylor series, just look at the first derivatives, and when you've got a system with 4 interacting variables with functional forms which include the variables themselves and these other sort of linking variables and time, then you can look at the eigenvalues of the Jacobian matrix of these things, and the very crudest thing you can do is say, okay, are those eigenvalues positive or negative? Are there positive eigenvalues, which means that aspects of the system will grow exponentially? What are the characters of fixed points? We can set the rates of change equal to 0 and look to see whether fixed points are stable or unstable. And some more recent research, which looks at approaches to modeling complex systems with many, many parameters, tells us that for physical reasons, good physical reasons, usually there are only 3 or 4 groups of parameters that control the way the system behaves. And in fact, what you have to do is transform the system out of the parameters you chose intuitively into a new state which is optimized so as to find the groups of parameters which are the controlling ones. I won't go into that at all, but that's the way we are. So the question we started with is, we talked about attractors. So is the trajectory of the human Earth system understood? And can we model it well enough to provide any useful guidance about things like the SDGs? My late colleague, Doug Cox, defined what he called quality survival, which could be our safe and just operating space. Is the trajectory of the human Earth system has to dwell in a part of the state space where population is bounded, wealth is sufficient and sufficiently spread to satisfy aspirations, adverse biogeochemical change is limited, and society in the main attains an open access order. So the question is, are we on a trajectory which is on an attractor like that? What do we have to change to make that an attracting state? So here are the conclusions. At the moment, the UN population projections say 9 to 11 billion. The difference of 2 billion is entirely the result of educating or not educating women around the world. So that's the difference it makes in the UN models. It implies that people have an income sufficient to limit fertility, which means about 5,000 US per annum. So even if the massive skewness in wealth today is reduced, it still means we have to grow the economy substantially. So we have to avoid then the negative impacts on the biospheric systems that we're using to support life. So the key focus is not, let's stop the economy growing. The key focus has got to be, let's find a way that we can grow the economy without screwing the planet at the same time. We can, for example, decarbonize the world economy today using current technology at a cost, but also with a huge benefit. So jobs, for example. But we're not doing that, and we're not doing that because of the ruling ideas of society, and if you like, this war between the nurture and the exploitation narrative. So we're currently taking choices that are pushing the trajectory in the direction of continued high carbon use, which is not to a state that we want to be. On the other hand, the economic forces are favouring decarbonisation. So while the politicians are still arguing about how much coal we should use or whether the future of the planet lies in coal, at least they are in Australia, the fact that renewables are getting cheaper and cheaper means that that's what's going to change the energy system. But you probably conclude that currently a safe and just operating space is not an attractor for the human Earth system. So the question for you guys, who you're going to be left with this mess, is what do you do to make sure that it becomes that? And the last slide, I think, does visualizing this whole thing as a complex system help at all? Well, we talked, I think, yesterday a bit about complex causality, the fact that when you have a complex system with lots of interacting bits, even at the highly emergent level, there are lots of interacting things there. It's very hard to know whether poking the system here will have the desired effect. It might pop out somewhere else over there. So complex causality has to be understood, and you can actually look at the system using a series of techniques. Gabby mentioned a few of them, causal depth and so on, which allows you to get some idea of how confident you can be that taking a certain action will have a desired effect, like an SDG. We need to drop down a couple of levels from that emergent level to actually model things that give us useful results. But if you lose sight of the fact that we're actually embedded in this larger interactive system, once again we can get the wrong answer. You've always got to be very careful when you've got a system which is part of a larger system, that what you do might look right, but bigger feedbacks from outside can screw you. So even teasing out these links and processes is illuminating. And we can actually do formal modeling, which we're at the moment trying to do, which I haven't talked about this in this talk at all. Okay, here we are. Thanks.